Welcome back to The Explainer, everyone. Have you ever stopped to think about how the entire fabric of our modern world might just be tied together by a single, seemingly random date on the calendar? Seriously, today we're unraveling the secret history hiding right behind one specific day. We're going to look way beyond the standard history books and discover how centuries of brilliant, incredibly interconnected mathematical thinking all pivot on this one exact moment in time. So let's just dive right in. The golden date is July 26th. And look, this isn't just any regular day. This is actually one of the most astonishingly concentrated dates in the entire history of mathematics. On this single calendar date, across wildly different eras, brilliant minds were either born or passed away, leaving behind the exact, precise ideas that built our modern reality. I mean, we're talking about a spectrum of human achievement that stretches all the way from the ancient geometry that draws shapes on your smartphone right up to the bleeding edge of quantum computing. We've got a timeline with four massive breakthroughs: 1271, 1852, 1925, and 1930. We're going to jump through time today to meet four incredible thinkers marking these exact years. They lived in completely different eras, on totally different continents, but you guessed it, they all share this one special date. Now, let's start with a bit of a paradox. Have you ever wondered how your phone screen makes perfect circles out of tiny, square pixels? Think about it for a second. If you zoom in close enough on your smartphone, or say a 4K monitor, you're going to see a rigid grid of millions of tiny, square pixels. So how on earth does your GPS map or your favorite digital art software render a beautifully smooth, perfect circle out of these jagged, right-angled blocks? Well, the answer actually goes all the way back to July 26, 1271, and a brilliant mathematician and astronomer from China named Zhao Youqin. Long before we had modern calculators, he wanted to find a much more precise value for pi, and he did this by employing what is conceptually really similar to the method of exhaustion. Basically, he showed us how to build a perfect circle by starting with just a simple inscribed square. He figured out that if you continuously double the sides of that shape, going to 8 sides, then 16, then 32, relentlessly calculating the perimeters by hand all the way up to over 16,000 sides, the polygon perfectly rounds out into a circle. By rigorously deriving these measurements without any modern tools whatsoever, he essentially handed us the foundational algorithmic steps that our modern computer graphics processors use to approximate and draw perfectly smooth digital curves today. Mind-blowing, right? The circle starts from the square ends in the circle. Zhao Youqin perfectly captured his own aha moment when he wrote that. It's just a profound reminder that advanced mathematics is so often just the pursuit of hidden, infinite patterns. He realized that if you push the geometry of a hard-edged square far enough, it mathematically surrenders into a perfect loop. Moving right along the timeline from 1271 to 1852, we're still on July 26th, but we're jumping forward over 600 years. Same date, completely different continent, and an explosive new era of industrial technology. Have you ever wondered how the exact right amount of electricity safely reaches the light bulbs in your house? When you flip a switch in your home, boom, the lights instantly glow. But think about the incredible tension of early electricity. How do you prevent a massive, incredibly dangerous amount of power coming from a city station from causing short circuits or huge voltage drops? How do you master the absolute mathematical nightmare of running parallel circuits so that one blown bulb doesn't plunge an entire city block into total darkness? The solution traces right back to a guy born on this exact date in 1852, Francis Upton. Now, obviously, we all know the name Thomas Edison, but Francis Upton is fascinating because while Edison famously relied on endless trial and error, Upton used pure equations. Upton was literally Edison's mathematical brainpower. Edison had the grand vision, sure, but it was Upton who solved the critical mathematics of high-resistance filaments. He calculated the exact dynamics of electric generators and parallel distribution circuits, making sure that voltage remained completely constant across a massive grid. His calculations were so flawless, in fact, that his own home became the first private house in the entire world to be lit by electricity. Without Upton's rigorous algebraic blueprints, our modern cities simply wouldn't have safe, scalable power today. He was the mathematical brain behind the very first glowing light bulb. And it's so true. Without Upton's algebra, Edison's bulb was kind of just a glowing parlor trick. The crucial takeaway here is that behind almost every great world-changing inventor, there is a mathematician working in the shadows, making the impossible entirely possible. Okay, Let's move forward again from 1852 to 1925. Just one date on the calendar, and we're seeing so many massive shifts in human history. We're keeping the momentum going by jumping to 1925, still July 26th, remember, but now we are exploring the very foundations of the digital age. How does a computer actually think to make a video game character jump exactly when you press a button? Have you ever wondered how a computer really processes those complex commands? Like when you're playing a game and you smash that jump button on a controller, how does the machine instantly process the complex logic required to make your character defy gravity on screen? How does a machine actually know how to evaluate a condition and execute a result? Well, the answer connects to an absolute genius who passed away on July 26, 1925, named Gottlob Frege. Interestingly enough, he wasn't trying to build computers at all. He was actually a philosopher and a logician. But he wanted to prove that all of mathematics could be reduced down to pure logic. So, to do this, he developed a precise logical system of rules called predicate calculus. By breaking down language and human thought into rigorous mathematical symbols, essentially creating the very first structured if-then statements and rules of quantization, he allowed abstract logic to be calculated exactly like numbers. This theoretical framework became the absolute rock-solid foundation for Boolean logic in computer science. It's the secret language, the fundamental architecture of the logic gates that literally all our microchips and software rely on to process information and think today. Every line of computer code you will ever write is secretly built on his logic. That statement just perfectly captures the sheer magnitude of his legacy. Abstract philosophical theory from the turn of the 20th century literally became the invisible architecture powering our modern internet, our apps, and our video games. Moving from 1925 to 1930, let's make our final time jump here, just a few short years later. We are staying right on July 26th, but we're arriving at the absolute bleeding edge of modern science. How do our newest, most powerful computers calculate millions of possibilities at the exact same time? We've talked about regular computer logic, right? The kind that operates in strict black and white true or false states. But what about the future? How do the absolute newest quantum computers leverage mind-bending concepts like superposition to exist in simultaneous states? This allows them to look at millions of complex, chaotic problems and solve them all at the exact same time. This deeply mind-expanding concept connects to an amazing mathematician born on July 26, 1930, David Foulis. Look, the subatomic quantum world doesn't play by normal rules. It is completely chaotic and totally counterintuitive. But Foulis helped create the intensely complex algebraic foundations required to actually measure and model this bizarre behavior. He helped map out a system known as quantum logic and orthomodular lattices. So in simple terms, he developed the specific mathematical rules for the quantum world. This allows us to predict a universe that operates on overlapping probabilities rather than strict certainties. His theoretical work literally gave us the blueprints we're using right now in cutting-edge labs to build the super-fast quantum computers that are going to shape our future. He gave us the mathematical rulebook for a universe where the impossible becomes possible. I absolutely love the weight of that thought. It just goes to show how human imagination, when paired with rigorous abstract math, unlocks a completely new way of understanding the physical world around us. Here we see our full timeline: 1271, 1852, 1925, and 1930. Let's move to our wrap-up and really synthesize these incredible leaps. Every single person we met in this explainer shared July 26 on the calendar, and just look at the scale of their progress. We went from a 13th century geometric circle in China to the electrical math that lit up a 19th century room, to the rigorous philosophical logic that powers our modern internet, all the way to the probability math of the quantum realm. They all shared one common thread. They looked at the world around them and rigorously mapped out the hidden patterns hiding inside the chaos. What pattern hiding in the chaos will you discover today? I want to leave you with this final provocative thought to chew on. If these brilliant minds could look at simple squares, delicate electrical filaments, and philosophical language, and completely rewrite the rules of our reality, what pattern hiding in the chaos will you discover today? Thanks so much for joining me for this explainer, and keep looking for the beautiful math hiding right there in your everyday life. Catch you next time.